Okay, last week of term, learning timetable number 6, AS Mechanics, and this is the last one for the summer now, so in the series, so 6 weeks or 18, you've done 18 exam questions. Okay, you're good at, should be good at M1 if you've done all of these and attempted all of these yourself by now. Okay, so I'm going to use a little bit of technology again here, and this is the worksheet, the 3 questions for this week. And how about this for technology? I'm just going to get rid of those 2, because I use a pair of scissors to cut them up, and we'll just deal with this first one first, okay? And it's about lobbing stones up in the air again. So, a stone is thrown vertically upwards at a speed of 16 metres per second from a point H metres above the ground. So we always draw a diagram. Here it is, there's my ground, this is ground level. Don't know why I drew that over there. And what we're going to do is we're going to go splat. That's what happened. And let's get some speeds on there. So U was 16 metres per second, the -1. V is 0 at this top point, isn't it? The acceleration is going to be -9.8. That's what we're going to use in our formulas. And the height here is there, and it hits the ground, so T is 4. Okay, at this point here, so it takes 4 sort of seconds, and we've got to find the value of H. Okay, so let's have a look. We've got U, we've got the time, so we've got U and T, we've got the acceleration A, and we want this distance here, S, as the displacement after this time. So it's easy, this has got to be, you list them out, it's got to be this formula. Okay, for part A. Alright, of course S, when we put all these numbers in correctly, S is going to come out negative, isn't it? Because it's a, you know, that is S equals 0, this is S equals minus, this highest point would be a positive S. Okay, so it should come out minus. If it doesn't, we've done something wrong. So S is equal to UT. So the initial velocity was 16 and it travelled for 4 seconds plus a half times -9.8, and you've seen me do these before where I just straight away just go combine all that and put -4.9 t squared, and t squared is 4 squared, so I'm just going to put straight to 16. Okay, so all of this, normally I would go, I'll put that in, -4.9 times 16. That's what we're going to do. So switch my calculator on. 64 minus 0.9 times 16 is equal to -14.4. So S is -14.4 metres. That's how tall that is, below the horizontal. And the speed when it hits the ground, we've got so much information now, we can use all sorts. We can put S into one of the formulas as -14 and find the velocity when S is -14.4. So we could use V squared equals U squared plus 2AS. We could use that, find the velocity. We've got that. We've got the acceleration. We've got the displacement as -14.4. We could put it in. A simpler formula actually is V equals U plus AT. I'm going to use that one. I've got the velocity. I've got the initial velocity, 16. I've got the acceleration, which is -9.8 times the time, which is 4. You can see here again, the velocity is going to come out negative, and so it should. It's going to come out negative because it's travelling in the opposite direction. If you did this here, when you square root, of course, you square root something, the answer is positive or negative. Well, it's the negative version that it's referring to. So 16 minus 9.8 times 4 is equal to -23.2. -23.2. So the velocity is 23.2 metres per second. All of the minus is showing us is this the direction it's travelling on, and that's the first one. Okay, fairly straightforward. It's just deciding what formula to use, isn't it? Is always the skill. Alright, so we've got that. Let's get rid of that now. Let's go for number 2. So this was the second one. Putting these on now. This is, you know, I said last week the same. That how you do these is, you know, is how good you get at mechanics. You've got to be able to resolve forces. So let's just put this one on and draw our proper diagram. Now I'm going to draw 2 diagrams here. I'm going to draw this one. I'm going to copy this one out. Q and P, and I'm going to put P on there. Okay, and I'm going to draw a rough diagram first, and then I'm going to adjust it. So 24 newtons, that's my mg. It says it has a weight of 24. It's not put that on there, so we're going to put that on. And this angle here is 30 degrees. Now remember what I did last week. I have my x and I have my y, and there's my right angle. Okay, and this is the 30 degrees here, and this is the adjacent force. Now I'm only going to do this once because it's, you know, it's exactly the same as in learning timetable 5. I'm going to, or 4, which 2 weeks ago, what is it? That we resolve this by simple basic trigonometry from GCSE, and that is that the cos of 30 degrees is the adjacent over the hypotenuse, which is x over p. So p cos 30 is equal to x, and likewise there, I'm going to do that quicker, p sine 30 is going to be equal to y. Now I've got that, I'm going to redraw that diagram. There's a diagram, that is Q. Now this here, this vertical force, I'm going to put there, okay? And that vertical force is P sine 30. This way is 24, and that way is P, the horizontal force here, which is P cos 30. All right. Now we've got to find out the value of P and the value of Q. Can't find Q just yet, but we can find P here. Let's do that. So now, because we've resolved this and got all the forces on, and it's in equilibrium, okay, so up equals down, left equals right, they're not moving, they are equal. By the way, this little hint here, you will have to resolve P into the I and J components. That's not on the actual exam question. I did that, I stuck that in for you, okay. So we've got P sine 30 is equal to 24, so P is equal to 24 divided by the sine of 30. Actually, sine of 30 is a half, so 24 divided by half is 48 newtons. That is P. Okay, and now we've got Q is equal to P cos 30, so Q is equal to 48 times the cos of 30 is root 3 over 2, you want to use that, so Q is equal to, keeping it nice, 24 root 3 newtons, okay, or whatever that is in the mark scheme. If it might give you that, or it might round it off, okay, and there we go, that's okay. And then the last one is, again, what I said last time is that Thursday's one, I had to take these, or I put velocity in twice there, sorry, I typed this out from the book. I had to put these in from the book because these weren't on the old M1 paper, so this is new, this variable acceleration. This particular question is interesting. It's a real life situation, but it's really important to understand the question of what's happening, is to make that link between what it's like as an actual diagram. So sorry, I'm just getting sidetracked. Oh, the computer's gone down. As what it's like, you know, in the classroom mathematically. So we're going to look at real life, but we're also going to look at it as sort of mathematically as just a graph. Okay, and at time t equals 0, particle leaves the origin, and so I'm going to draw that here. There's the origin, and moves along the x-axis at time t seconds, the velocity of v is v meters per second, and blah blah blah. Now it tells you that v is equal to 6t minus 2t squared. Okay, you can see here that this is a negative quadratic, so it's a smiley face. It's also when t is naught. Okay, put t is naught into there, v is naught, so it's actually starting from the origin there at 0, you know, with a velocity of 0 at time 0. And because it's a quadratic, it's symmetrical, isn't it? So it's going like that. Okay, so it's accelerating, but that acceleration is decreasing. The rate of acceleration is decreasing until it reaches a maximum velocity, and then it starts to decelerate. Okay. All right. Okay. So the velocity comes down. So there we go. Right. The maximum value of v, and you can just now you can see that we don't need to do mechanics on this now and equations of motion and so on. We can just do normal maths on it. The maximum volume of v, okay, is the top of the graph here, isn't it? And how do we find a maximum point? It's when the gradient is 0. So in other words, when dv by dt, the acceleration becomes sort of 0 instantaneously here. So dv by dt, differentiate it, and then we'll find that's the gradient of the line, isn't it? And we'll find that stationary point, and that is 6 times by the power, not 1 off the power, so minus 4t. Okay, and if we put that equal to 0, because if we want it when the gradient is 0, 6 minus 4t, we can say 4t is equal to 6, t is equal to 6 divided by 4, which is 3 over 2, which is 1.5 seconds. So it reaches that point at 1.5 seconds. Okay, you can, because it's a quadratic, we can factorise that and put it equal to 0 to find these 2 points, but we know that it's a quadratic, it's symmetrical, so that's going to be at 3 seconds, isn't it? T is 3 there, but if we factorise it, this, and just take out t, we get 6 minus 2t, there we go. And you can see here when t is 0 and when that is 0 is when t is 3. Okay, so we've got that. And the time taken for p to return to here is, it's just it's just that then, isn't it? Okay, the time taken for p. I thought it might be like the distance, you know, covered or something like that, but it's more simple than that. It's just simply, 3 seconds. Okay, in 3 seconds, is that right? Oh no, 5, it can't be right. Okay. No, that's sorry, now I'm getting mixed up here. So this is where, we do have to, we do have to integrate that up, because what's happening at this point, this is when the velocity is 0, but it's not returned back the display. We want it when the displacement is 0. Okay, so right, let's sort of scrap that and let's do this then. So if we integrate this up, remember we've got v, a and s, and we're going to integrate up. So we're going to go up 1, so add 1 to the power, divide by the new power, so we've got 3t squared. Okay, so we've got that. And this one, add 1 to the power and divide by the new power. So we've got minus 2t cubed over 3. Okay, so we've got that. And we've got to have a plus c, but we know that at time t equals 0, s equals 0 because it was at the origin. So So therefore, that is the formula for the displacement, okay? And we want it, the time for when the displacement is 0. So actually what we're going to solve is when s is 0. So if we put, so this is part B, so we've got part A, the maximum velocity. Oh, sorry, I'm doing a terrible job here. Let's go back. We've got, I've not even answered this flaming question, okay? 1.5 seconds in, it reaches its maximum velocity, but we've got to put that into this equation, haven't we? So 6, I should read the questions before I go through them with you, times by 1.5 squared. That's the maximum velocity. So I'm putting 1.5 seconds to reach the maximum velocity. We've got to put it back into the equation. So I'll do that bit first, sorry. I've done 3 of these on the run and my brain is scrambled now. Too old. And so we've got 9 minus 2 times 1.5 squared is equal to 9 over 2. Okay, so velocity is 4.5 meters per second to the minus 1. That's part A. Sorry, I'm back on track now. And we want the display, so we've integrated up to get the displacement. We want it when the displacement is 0, so 0. And we're going to use this formula. C is 0, so we don't need to use that because S was 0 and T was 0. So we've got 3t squared minus 2t cubed over 3. Now, what I'm going to do is I'm going to times everything by 3. Okay, so now I've got 0 is equal to 9t squared minus 2t cubed. I'm going to factorise, okay, and take out t squared. Is that? And you can see that this must be, it happens when t is 0, but also when 9 minus 2t is equal to 0. So rearranging that is when t is 4.5 seconds. Okay, so it's at the origin when t is 0, but also when t is 4.5 seconds. Okay, just solving that equation, so 9 divided by 2. Alright, so that's why that's 5 marks, because you've got to integrate up and then solve this here. Alright, okay guys, obviously the temptation is always to take that over to the other side, isn't it, and then divide by 2 and divide by t squared, but you shouldn't do that because you lose some of the roots. You lose the t squared. We know we don't need that for this answer, but it's just not the proper way of doing it. This is the proper way of doing it. Okay, so it takes 4.5 seconds for P to return. I've done that one and I don't think I made a mistake. All done.